This is section 10.2b, continuing with parabolas. Today we're going to go through some problems involving parabolas and some applications as well. So let's look at an example of trying to find the standard form when we're given certain bits of information. Find the standard form of the parabola with vertex 2, 1 and focus 2, 4. Now you should be able to do a rough sketch and then proceed from there. But I'll just walk you through the rough graph part of it first, because this is always a good first step, and this will just be a reminder of why it's a good first step. Let's graph our givens. We know that we can plot the points 2, 1 and 2, 4 because we know the vertex is 2, 1 and the focus is 2, 4. And this automatically tells us where the curve is, because we know that the nature of a parabola is such that every point on the parabola is equidistant from a focus and a directrix, so it curves this way from the vertex towards the focus and around it. And now at this point you can clearly see that p equals 3, because if p is the distance that I'm tracing right now with the mouse arrow, if p is this distance from 2, 1 to 2, 4, well, the only way they differ is in their y-coordinate. And the difference between 4 and 1 is 3, therefore p equals 3. Why is it positive 3? Because it's going upward, all right? And since it's 4 minus 1, it's 3. And negative 3 would be going downward, right? But this is an upward facing parabola. Now pause the video, do the rest of this problem yourself, and then resume when you have an answer. So after we do our rough sketch, plug in the information into the vertical standard form. And of course you should know why we use the vertical standard form rather than the horizontal standard form. That clue was given to us by doing the sketch, because we could see that it's an upward facing parabola, therefore vertical. And the vertical standard form is x minus h squared equals 4py minus k. Now we found p from the sketch, therefore we just fill in 3 for p. 4 times 3 is 12, and then my vertex, which is given to me, is 2, 1, and that corresponds to hk. So x minus 2 is x minus h, and the y minus 1 is the y minus k. So that's the correct answer to this problem. Let's do another example like that. Find the standard form of the parabola with vertex negative 3, negative 1, and directrix x equals negative 1.5. Okay, so this directrix is a vertical line. The vertical line x equals negative 1.5. And you should review your notes of what a directrix is. It was explained when we started with parabolas. And you should have those sketches written down. That should be part of your notes. So at this point, you do have all the information you need to solve this problem. You're going to need to think about it a little bit, because the focus isn't given to you, but the directrix is. That's a bit of a hint right there. Alright, so pause the video, do this on your own, then resume when you have an answer. So first step, as always, we're going to sketch a rough graph. And we plot the points that we know. So negative 3, negative 1 is the vertex that's given to us. And the line x equals negative 1.5 is the directrix. So from the definition and nature of a parabola, we can automatically sketch it as a left-facing parabola. The curve, as you remember from our definitions, curves always go away from the directrix. And that's why, even without worrying about being perfect in the way that I trace this curve out, the important thing isn't to have a perfectly accurate graph. The important thing is just to sketch so that you have an idea of what's going on and which standard form to use. We can calculate from this sketch the fact that p equals negative 1.5. Now how do we know that? Well, I know from the definition of a parabola that every point on the curve is equidistant from a directrix and a focus. Well, then this special point here is the vertex. And that point still fits the same criteria. That point, the vertex, is going to be equidistant from a directrix and a focus. So if the distance between the vertex and the directrix, that distance which I'm tracing right now with the mouse arrow, right? If this distance that I'm tracing with the mouse arrow represents the distance from the vertex to the directrix, well, that is obviously a distance of 1.5, a distance of 1.5, because the difference in the x-coordinates, -3 here for the point and -1.5 for the line, the difference in the x-coordinates is 1.5. Right, so the distance of the directrix to the vertex is 1.5, and therefore, since every point on a parabola is equidistant from a directrix and a focus, therefore the distance from this vertex to the focus, which I haven't drawn yet, that distance must also be 1.5. And why is it negative 1.5? It's negative 1.5 because we have a left-facing parabola. Therefore, I can draw in the point and its coordinates. And these coordinates and this point I deduced entirely from the givens and from the sketch. All right, so why are the coordinates negative 4.5, -1? Well, I know that the y-coordinate is -1 because this is a horizontal parabola. Therefore, the axis of symmetry is horizontal. Okay, so they're going to have the same y-coordinate, both focus and vertex. And the only difference in x-coordinates, when we're comparing the vertex to the focus, it's going to be negative 1.5, which we already proved because that's the same as the distance of the directrix to the vertex. So from this, I can conclude that p equals negative 1.5, and I plug in the information into the horizontal standard form. Why the horizontal standard form? Because this is a left-facing parabola, therefore horizontal. And so I use the horizontal standard form, y minus k squared equals 4p x minus h. Filling in negative 1.5 for p, 4 times negative 1.5 is -6. And then filling in the vertex, -3, -1 for the h and k. Well, y minus k is y minus -1, therefore y plus 1. And x minus h is x minus -3, therefore x plus 3. And this is the correct answer. Next, we're going to do a little bit of show and tell. Remember when you were in kindergarten, and sometimes there was a show and tell activity where a student, the child would bring in something interesting to show, maybe something from his house, a toy or a pet, and then explain it to the class, tell interesting things about the class. So a little show and tell here. I'm going to show you a flashlight and solar cooker and tell you about it. So one common application of a parabola in real life is a parabolic reflector. And the way a parabolic reflector works is that whatever rays are emitted from the focus bounce off the reflector outward in straight lines. Or likewise, whatever rays come into the parabola bounce off the parabola into the focus. All right, so parabolic reflectors are used a lot in electronics. For example, flashlights work this way, headlights, solar cookers, the way they catch sunlight, and even satellite dishes, which is a parabola that's been rotated 360 degrees to give you a three-dimensional parabola. They also work with this principle. So I brought a couple examples of parabolic reflectors. This here is a solar cooker. Very simple. You can just make one out of cardboard. In fact, some of you may have done this before in the Boy Scouts, or maybe you did it while you were camping, or maybe you've used one before. On a hot day in the summer, you can use it to cook a hot dog. In a really hot day, let's say you're in Arizona in the desert, you could use it to boil an egg. So it's pretty useful. I'm just giving you different views of it. We can see the parabolic shape, and we can see that this is it goes along an axis, and so you'd put the food lengthwise in the middle to cook it. But it does work. You can try to make one of these on your own, and you'll see, especially if you experiment with different heights of where to put the food, you'll see that it works. For example, you could put the food low, you could put it a little higher, and eventually, with trial and error, you're going to find the perfect focal point. Okay, so the way that this cooker works, it's the same principle. The light rays come in and they bounce off the foil into the focus. All right, since this is a parabola, there's a focal point, and all the sun rays come in at straight lines into the parabola, and they get reflected all towards the focus, which is where you'd put the hot dog or the egg. Another example of a parabolic reflector is this flashlight. Okay, this flashlight, you've definitely seen flashlights before. There, I'm turning it on. Well, the reason flashlights are able to illuminate better, even when they don't have, really strong batteries, is because the inside of the flashlight is a parabolic reflector. So here's a little close-up of that. We can see the bulb, and if you look closely, you'll see that the reflective surface is a parabolic reflector. So all of the light beams that radiate out from the bulb, which is placed exactly at the focus of this parabola, all of those light beams bounce off the reflective surface and go outward in straight lines. So the parabolic reflector of a flashlight concentrates the light. The headlights on a car also do the same thing. They do the same exact thing. And so does a satellite dish, because they all operate with the same principle. The light rays come in, so the light rays come in and they go to the focus. Light rays come in and they go to the focus. Come in, go to the focus, come in, go to the focus. Likewise, as would happen in a flashlight or a headlight, the light rays are emitted from the focus and bounce outward in straight lines, and that gives you a more intense light. So hopefully this helps to understand a little bit how parabolic reflectors work. It's an application of parabolas. The very nature of the shape of a parabola, being that all points on it are equidistant from a directrix and a focus, that makes the curve such that all rays going into or out of the parabola converge on the focus, or they go out in straight lines. Okay, so this is how parabolic reflectors work, and maybe when you go home, you can look around the house for examples. Maybe you've got a flashlight, you can look at the curvature of it. Or maybe you can go outside to your car, take a look at the interior of the headlights. In any case, there are parabolas all over. Maybe if you have a satellite dish or you've seen one before, you can also notice how the focus is placed at the point where the rays are collected. This is another good example of a satellite dish. Actually, this is the satellite dish at Rim of the World High School, where our girls volleyball team won one of their playoff victories. And here we can clearly see the parabolic shape, and we can also see that the receiver is exactly where the focus is of this parabola. So it's a pretty good example of a satellite dish, and this is a good application or a good way to remember how foci act in parabolas. This is a satellite dish. Actually, I took a picture of this at a house that's right across the street from the school, so I wonder if when I stepped into their driveway, they might have thought I was like some kind of spy taking pictures of their house, or maybe they thought I was some kind of FBI agent investigating them. I don't know. I just took a photo and got out of there, but that's definitely not an illegal activity. It just probably freaked the neighbors out a bit. Anyway, this is a satellite dish, and I'm sure you've seen this before, DirecTV, you see these satellite dishes. And if you follow the mouse arrow, you can see that the shape that I'm tracing around, this is a three-dimensional parabola. And so it has the same basic shape as the interior of a flashlight or a headlight, but it is a shallower dish. And so this receiver here, this receiver is at the focus of the dish. All right, so the signals are gathered by the dish, they come in at straight lines from the satellite, and then they all bounce off the dish's surface into this focal point, and that's the receiver. Here's the classwork. page 740. Please write those numbers down, and we'll see you in class.